Hi, today we're going to discuss heating curves. I'm going to look at water as my example, and I have behind me a graph which looks very similar to the one that's in your notes. I'm going to walk through and explain what it is. So let's imagine that on this axis we have temperature. Now I've marked two important temperatures, 0 degrees Celsius, which is the melting point or the freezing point of water, and 100 degrees Celsius. And on the bottom axis I've marked heat. And this could be Q, heat going in, or it could even be time if we have our sample on something like a hot plate or a stove, because as time goes on, more heat goes into the system. So as we're moving along, we're adding more and more heat. Now, on the left side here, I have a line which is a diagonal line with positive slope, and it's temperature and Q, which means as we add heat, as we add Q, the temperature goes up. So this right here makes perfect sense. As we add some heat, the temperature is going up. And this right here is the solid phase of water that we call ice. So if I start down here at a temperature of minus 15 degrees Celsius and I add heat to the ice, the temperature of the ice slowly goes up until it reaches 0 degrees Celsius. Now at 0 degrees Celsius, something happens. As I continue to add heat, the temperature stays constant. And what's going on here is that the ice is melting. Now, if I add more heat, I can't raise the temperature of the system, because adding more heat instead of raising the temperature just melts the ice faster. So a phase change occurs at constant temperature. That's the melting or freezing point. And that's why a cooler or an ice chest work. When you put ice in there and the heat leaks through the insulation and begins to melt the ice, the temperature of that melting ice is 0 degrees, and it stays at 0 degrees until all of the ice is melted. Now, at that point, all through this horizontal line, we're changing the phase from 100% 0 degree ice to 100% 0 degree water. So we've gone from 0 degrees to 0 degrees, and all we've accomplished is a phase change. But it took a lot of heat. It took a lot of heat to do that. And that heat is called the heat of fusion. There are 333.6 joules of heat required to convert 0 degree ice into 0 degree water, and that's for just 1 gram. All right, at that point, we now can warm up our water. So we start with 0 degree water, and we use Q equals MC delta T. The C for water is 4.186 joules per gram degree Celsius. Some references will have it different, and that's because really it does vary with temperature. This is about 60 degrees Celsius. It's right kind of in the middle between freezing and boiling. But anyway, so now we're back to what we understand as we are adding heat on this lower part of the lower axis. As time goes on, we add heat, the temperature begins to rise. And at a certain point, the temperature has risen to 100 degrees Celsius, which I marked over here, and that's the boiling point of water. At that point, we reach another phase change. We start with 100 degree water, and over here we end up with 100 degree steam. You may have seen before, if you're boiling a pot of water and if you had a thermometer in it, you would see that the temperature of the water is 100 degrees, and you can't get it any hotter than 100 degrees. And that's true whether it be in a lab or in a stove. Whenever the water is boiling, it's in this constant temperature range right here, and you cannot raise the temperature until you reach 100% vapor, which hopefully that means that doesn't happen, because that means you boiled the pan dry. But if we were to have captured that steam and had it in a container, we could then add more heat to it and raise the temperature of that steam. And here in the South, we don't see this very much, but up north, they actually do have steam boilers to heat apartment buildings and things like that. And if you've seen on television, the radiator mounted under the window, that has high pressure, hot steam in it to heat rooms during the wintertime. So there are some cases where you might encounter high temperature steam, hotter than 100 degrees Celsius. But in the South, not very often. When we boil the pan dry, that means we're in trouble. But what we have to do if we want to go from this point A to point B, which I've identified here, point A is 5 grams of ice at minus 15 degrees Celsius. Point B is the same 5 grams of steam at 120 degrees Celsius. We have to go through several steps. The first step is we have to warm the ice to melting point, to 0 degrees. Then we have to melt it to get 0 degree water. Then we have to warm the water to 100 degrees. So we have 100 degree water. And then we have to evaporate it or boil it. And then we have 100 degree steam. Then we have to take the steam and raise its temperature to 120 degrees. Each of those is in these equations right here. So right here, we have warm the ice, Q equals MC delta T. So we have 5 grams of ice times 2.04 joules per gram degree Celsius times 15 degrees Celsius. And the 15 degrees is the final temperature of 0 degrees minus the minus 15. So 0 minus a minus 15 is just 15. So we warmed it 15 degrees Celsius. Then we melt the ice. There's no delta T here. So it's just 5 grams times the heat of fusion, 333.6 joules per gram. Then we take our water at 0 degrees and we warm it to 100 degrees. So 100 degrees minus 0 is 100. So we have 5 grams times 4.186 joules per gram times 100. Then we have to boil the water. And again, there's no delta T here. We just use the heat of vaporization, 2,258 joules per gram, which is a staggeringly high amount. I'll talk about it in just a minute. 5 grams times 2258 joules per gram. And then lastly, we have to go from 100 degree steam to 120 degree steam. The specific heat of steam is 2. So we have 5 grams times 2 joules per gram degree Celsius times 20 degrees. That's 120 minus 100 where we started is our delta T, 20 degrees C. So 5 steps, each individually very easy. You just have to do them all and add them all up. So while this is a tedious process and long and involved, it's not actually very difficult. No individual one of these steps is any different than anything you've learned so far, other than the heat of fusion, or pardon me, the heat of vaporization and the heat of fusion. And those are pretty straightforward. You just take the value times the number of grams you have, and that's it. Just add it in. While we're on the subject of the heat of fusion and the heat of vaporization, 333 joules per gram is pretty high. That's almost as high as the amount of heat it takes to raise 0 degree water all the way to 100 degrees, which is only 418 joules per gram. I got that by multiplying C times 100 degrees. So 4.186 times 100 is 418, 419. So the amount of heat that can be absorbed by ice is quite a bit. Okay, almost as much heat as it takes to bring the water from 0 to 100 degrees, but not quite. On the other hand, the heat of fusion or heat of vaporization is very high, 2,258 joules per gram to take 0 degree water and turn it into 0 degree steam. What that means is, in addition to having to put that much heat in to vaporize it, it also means that if it vaporizes on its own, let's say evaporation, it takes that amount of heat with it. That's one of the reasons why when you get out of the pool or you get out of the shower, particularly the pool, even if it's very hot outside, you get out, the water evaporates off of your body and it carries that much heat, which is 5 times as much heat as it takes just to warm water from 0 degrees all the way up to the boiling point. It's 5 times as much. So it's a huge amount of heat that it carries away. So even a little bit of water evaporating off of your body, and you get that chill from the evaporation. All right. The same thing when it condenses is also true. a little bit of steam condensing on your body gives off that much heat to allow it to condense into liquid water, which it does because your body is cooler than the steam. So getting in front of, say, the steam on a tea kettle or something like that can burn you much, much worse than even spilling the boiling water on you to begin with, because there's 5 times as much heat in a gram of steam as there is to heat up a gram of water all the way from 0 up to the boiling point. So these phase changes, in this case, liquid to gas, and in this case over here, solid to liquid, involve huge amounts of heat.